Welcome to the chemistry walkthrough. In this session, we will learn how to read a concentration time graph. Concentration time graph surely showing the relationship between concentration of a product or reactant versus time. So these two are the typical example that we can understand. On the left-hand side, we have the concentration time graph of the reactant versus time. Well, this one is quite easy to understand. At the very beginning, the concentration of the reactant is quite high. After some time, when the time goes by, you notice the concentration of the reactant turns to 0 at the end. Well, in this case, it's not dropping on a slope as a slope. It's dropping exponentially. So you will notice it's a curve. Well, similarly, the products is similar, but in the products case, it's just the reverse. At the very beginning, products concentration is 0. After some time, the concentration of the product increase until it reached to a certain time. Then when all the reactants are finished and all the products are formed, then the time taken, the time of the reaction will simply finish here. So when we put the two diagrams together, it will show a similar diagram like this. So you notice when we are dropping like this purple curve, all the concentration of all the molecules of the A, which is the reactant, are at the highest level. But when time goes by, the concentration of the reactant A will simply drop and drop until 0. In reverse, B, at the very beginning, the product is 0. But when we continue, when time goes by, the concentration of the product increase, and then until it reach a maximum point, okay, then the reaction simply stopped here. So you notice these two curves should be quite similar, okay? But in this case, we are talking about a reaction simply at A converted into B. But if we have a case A turns to 2B, then the rate of this, the rate curve of this B will be significantly different. Well, we will talk about this in our classroom time, so please pay attention on it. So let's learn how to interpret a concentration time graph in full detail. A concentration time graph can usually be represented like this. Well, when we look at the graph, concentration time graph, say this is a product's concentration time graph, you'll notice at a certain point, the concentration of the product will reach to a very steady state. So this implies it's the end of the reaction. And when we look at this point, when we look at this point, the concentration means the final concentrations of the product. And at the same time, the time taken right here is the time taken, the total time of the reaction. So this point simply represents the end of the reaction. So if we want to calculate the average rate of the reaction taken, then we simply use this reading. Say this reading is delta P, and this reading is T. Okay, so average rate is simply equals to delta P over T. In this case, P, as what we have mentioned before, okay, is a P product's concentration at the final state minus the product's concentration at the initial state over time. Well, when we're talking about average rates, that means starting from the very beginning. So this value, the concentration of the products at the initial state, should be equal to 0. So in this case, we simply calculated like the concentration of the product over time. Then this is what we call the average rate. Well, in this diagram, it's not only telling us about the average rate of a chemical reaction. If, say for example, I want to know at a particular instance, say when the T become T prime in this case, I want to know the rate at this point. So what should I do? Well, we can still use the concept change delta P over delta T to calculate it. But what if this process is really short? Okay, I want to know at this particular instance there's a change. Then what should we do? Then we regard this speed or rate as what we meant by instantaneous rates, the rates at that particular instance. Seems a little bit difficult. So let's look at this example. Well, let's use this example to illustrate what is meant by instantaneous rate. Say you are going to travel through, or you're traveling through a fast-moving train. Well, at the very beginning, when the train is not moving at all, the speed at that particular moment is 0 km per hour. But when you travel, say 5 minutes later, it moved to a speed up to 430 km per hour. Well, the speed here measuring is not the average rate, but rather is what we call the instantaneous rate. That means the rate at that particular instance. So how can we calculate the instantaneous rates and the initial rates of a chemical reaction? Well, we can make use of the concentration time graph to help us. Let's look at this one. This is a typical concentration time graph of a product versus time. At the very beginning, this curve starts with 0 and then it reached to a maximum point. That means the chemical reaction has ended here. So when we want to calculate the initial rate, we are taking the instantaneous dimension. That means if you are good in mathematics, you should still remember what we call the differentiation. Okay, so at this moment we are doing dP over dt. This is the rate of change of product's concentration at a particular short period of time. So in this case, we are talking about the initial part, so it's almost like a 0. So this part, it is what we call the initial rate. Initial rates, the rates at the very beginning of the reaction which follow this linear dimension. So at t equals to 0, the rate is like this. So this line is simply drawing a tangent to this curve. Okay, just like in a differentiation, this dP dt is actually the slope of that particular tangent line. So when we draw this tangent line and then we get 2 points from this tangent line and then we calculate, then we will obtain the initial rate. That means the rate at the very beginning. But when time goes by, you'll notice the slope of this tangent will become smaller and smaller. Okay, similar, we use the method of differentiation. Okay, we can use the dP dt to calculate the slope. Like at t1, at time t1, we can calculate by using this tangent method. So get 2 points and then calculate the slope of this tangent, and then we will know the speed at this particular instance. Okay, similar to time t2 and t3. Okay, and at the end, you'll notice the last point. If we draw a last tangent right here, t4, that means this is already the end of the chemical reaction. When we calculated t4, the slope at this part will become 0. So we will notice actually the rates of the reaction can be calculated like this. And you will notice At the very beginning, the slope of this chemical reaction, that means the rate at of this chemical reaction is very fast. But soon it becomes slower, 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 and eventually it gets to zero. Concentration time graph itself is very, very important when we are studying the rates of reaction. We will learn a lot more about the rates of reaction on the curve and some other calculation later. So, as a conclusion to this part, we have learned how to read a concentration time graph. We know how to calculate the average rates of a chemical reaction. We know how to calculate the initial rates by looking at the slope, the slope of the tangent line at time t equals to 0, and we know how to calculate the instantaneous rate by calculating the slope of the tangent at a particular time t. So, thank you for watching.